right, welcome to YouTube Lecture Notes 1. In order to complete these lecture notes, you will just need your printout of the lecture notes that you can follow along with and something to write with. Today we're going to begin by talking about measurement, and you've probably done quite a bit of measurement in other science classes before, but it's a good place to start because measurement is very important in chemistry, as it is in all science classes. If we don't take good measurements, then we don't have accurate and precise data in order to work with for our calculations. So let's just do a little bit of review on the best way to measure using different devices. Let's say we're using a ruler to measure with, and we want to measure the length of this line. Okay, you can see that the ruler is in millimeters. Okay, that's our unit. And we have marks that are going to guide us in order to measure this to 3 point, and I think this is the 0.5, 6, 7, 8. So we can say with certainty that this line is 3.8 millimeters. We are able to record our measurements to 1 digit of uncertainty. Okay, so you will have one estimated digit in your answer, and that is left up to you as the scientist. So if I looked at this line, I would say it's definitely 3.8, and I'm going to say it's about 3.82 millimeters long. Maybe you picked a different estimated digit, and that's just fine. Let's label this as your estimated digit, or your digit of uncertainty. Okay, so that's how we would properly use a ruler. 3.82 millimeters. Now, what if we're trying to measure the volume of something? And we're going to measure in a graduated cylinder. When you look at a graduated cylinder, you always want to look at it from eye level, and you're going to see that the liquid kind of takes a sloped form, and that's called a meniscus, that sloped line. You will always measure the volume of a liquid from the bottom of the meniscus. Okay, so let's try to do that. Here's our markings. These big lines are by 30. This would be 35, 40. So we know we're at least above 35. We're even a little bit above 36. So let's say we are 36 point, and you get to decide the digit of uncertainty. Okay, I'm going to say 36.7 milliliters. Okay, and again, that is your estimated digit. Always measure to 1 digit of uncertainty when you're taking measurements. Okay, if we move on to the next section, you guys took some notes on significant figures in your before class notes. So let's go over a few of those examples together. Here are the rules that I like to use for significant figures. Number 1 is really easy. It says non-zero numbers. So anything that's a number besides a 0, it's always a significant digit. Number 2, leading zeros are not significant. Okay, we'll talk about an example that fits that rule in just a second. And rule number 3, zeros after the decimal and after a sig fig, so they're like sandwiched in between, they are always significant as well. So I think the best way to look at sig figs is to jump into a few examples to have you get the hang of it while we're doing them together. So let's look at letter A. Okay, how many digits do you see that are non-zero numbers? I would count them as 1, 2, 3, 4. I have 4 significant digits in that number. And if we want to write a rule kind of to go with it, I'm going to write that these are all non-zero. None of them are the number 0, so they are all significant figures. Okay, let's look at letter B. I have this 0, but it's after the decimal and it's after a significant figure. So it's kind of sandwiched in between other significant digits. So it matters. I have to count it as a sig fig. This one also has 4 sig figs. And I'm going to write that it's a 0 after the decimal to try to remember that it's sandwiched in between. All right, let's go on to letter C. The most common answer that I would get for letter C is it either has 1 sig fig or it has 1, 2, 3, 4, 5, 6 sig figs. We have to decide, are those zeros significant or are they not? Okay, this is an example of rule number 2. These are leading zeros. They're just placeholders. They are holding the hundredths thousandths place. Okay, they're just holding the place for this number. This example has 1 sig fig. The others, the zeros, are just placeholders. Okay, let's look at letter D, 12.20. Is this 0 significant or is it not? I'm going to give you a second to think about it. Letter D has 4 sig figs. This 0 is after the decimal and it is after another significant figure. This 0 matters. Another way to think about it is the scientist purposely recorded this measurement to 12.20. Not just 12.2. They took the time to add the extra 0 because it matters. It's significant. It is after the decimal. Okay, go ahead and look at letter E. How many sig figs are in letter E? Letter E has 2 sig figs. 1, 2. The 3 and the 4 are the significant digits. These zeros are placeholders, just like in letter C. They are holding the place for those 2 digits. Okay, so you will get some practice with counting sig figs in your homework. You'll do some examples that are just like these. And it just takes a little bit to get the hang of counting them, but once you do, it is pretty easy. Okay, remember that if they're actual digits, they matter. If it's sandwiched in between, it matters. It's a sig fig. And if it's a placeholder, if it's a leading 0, like in letters C and E, those are not significant digits. So why do we care about sig figs in the first place? Okay, why are we taking the time to learn what significant figures are? I would say the main reason is to be able to report the numbers that we get in our calculations to an appropriate degree of precision for the instrument that we are using. So for example, if you told me that your pencil was 10.34 centimeters long, I would say that's appropriate because we probably have a measuring device that can record that number of significant digits. But if you told me that your pencil was 10.34584930698 centimeters long, I would say, how did you get that? Where are these digits coming from? It would not be appropriate to report the length of the pencil with those type of digits because we can't measure to that degree of precision. Okay? Now for grading in this course, if we are specifically practicing a problem that's asking about sig figs, it is expected that you use the correct number of sig figs, or that you have sig figs in mind in order to get the problem correct. Later on in the course, if we are doing labs and homework, you will not be graded specifically on sig figs, but you should do your best to round to one estimated digit. Okay, so don't give me answers, or don't give your teachers answers like this. Instead, think about what would be appropriate for the measuring device that we are using. All right, let's move on to scientific notation. Okay, so scientific notation is a method for writing very large or very small numbers. Okay, so if we look at this example, it says there are about 20, I don't even know how big that number is, particles in a breath of air. Okay, that's a lot of zeros to write out, and that's a big number to try to read. Okay, if we use scientific notation, we could say there's 2.0 times 10 to the 22nd particles in every breath of air. These two numbers are the same. One is in scientific notation and one is not. So it's a method in order to write very large or very small numbers. Okay, it's pretty easy to put a number in scientific notation, and here's the rule of thumb that I usually use. I usually say to make your number between 1 and 10, then count the decimal places. Okay, so let's try this. I have a really big number. Let's see, that'd be 254 billion. Okay. I'm going to put my decimal place between the 2 and the 5 and make this 2.54. Okay, that follows our rule. It's between 1 and 10. Times, and I need to see how many decimal places I moved my decimal point. Okay, so we're going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This would be 2.54 times 10 to the 11th. Okay, let's do letter B. I need to make my number between 1 and 10. So I'm going to stick my decimal right here. 4.32. 1, 2, 3, 4, 5. This is going to be times 10, and this is going to be a negative exponent. Numbers that are less than 1 will get negative exponents for scientific notation. Very small numbers, 0.000432 is less than 1. It's going to get a negative exponent. Numbers that are greater than 1, like letter A, 254 billion, it will get a positive exponent. Okay, so you'll get some practice with those in your homework this week. Let's practice going the other direction. So I have 4.5 times 10 to the negative 8th. Okay, so if I wanted to put this in standard notation, I would have 4.5. Okay, because this is a negative exponent, I know that my number is going to be less than 1. I need to move this 8 jumps. 1, 2, 3, 4, 5, 6, 7, 8. And I would fill in with zeros. And that would be my answer. Okay, so the number should come out to be less than 1. Let's try letter B. 5.69 times 10 to the 13th. Okay, so I need to jump 13 places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, and fill in with zeros. Okay, you can add your commas if it makes you feel better. And there's our answer. So you can go both ways with these. Okay, the last thing we're going to look at today is converting in the metric system. Okay, we're going to learn an easy trick today for converting quickly between units. Next week we'll learn another method. Both of these work for units in the metric system. This one's just quick and kind of fun. So I like to remember a saying, and it goes like this. King Henry died. King Henry died unexpectedly. Drinking chocolate milk. King Henry died unexpectedly drinking chocolate milk. Now, what's cool about this saying is if you can remember it in your head, when you're trying to convert units, the first letters, King Henry died unexpectedly drinking chocolate milk, those line up with the prefixes in the metric system. K stands for kilo, hecto, deca. We're going to skip U for a second. The next D is deci, centa, and milli. U stands for units, okay? And our base units in the metric system are meters, liters, and grams. King Henry died unexpectedly drinking chocolate milk. Okay, so let's jump into an example and I'll show you how handy this is. How many grams? We want to know grams. How many grams are in 56 milligrams? Okay, 56 milligrams is where I'm starting. So I want you to put your pen on milligrams, and we're going to count how many jumps it takes to get over here to grams, because that's what we want to find. Okay. Let me do this in a pencil so I can erase it for the next one. So if I'm here at milli, I'm going to jump 1, 2, 3 places to the left to go from milli to grams. Okay, so you're going to do that in your number. Where's my decimal if I don't have one? Always here at the end. I need to jump 3 spaces to the left. 1, 2, 3. Fill in a 0. So here's your answer. 0.056 grams. That's what I wanted to find. Okay, let's do another one together. How many meters, that's what I want to know, are in 45 kilometers or kilometers? So we're starting in the prefix kilo, and I want to convert to meters. I put my pencil where I'm starting, and I'm going to jump to meters. 1, 2, 3 spaces to the right this time. So let's do that with our number. I have 45, my decimal's here at the end, and I need to move it 3 jumps to the right. 1, 2, 3. So I should get 45,000 meters. I'd like you to take a second to try the last one on your own. Convert 230 deciliters to liters. Okay, so don't let the order confuse you. We're starting in deci, and we want to convert to liters. So I need to move 1 jump to the left. So I'd be here, and I'd move 1 jump to the left, and I'd end up with 23.0 deciliters for my answer.